All right, how we doing? Ready for your exams to get back? Yeah, kind of dying to know how you did? Yeah, I'm with you. Me too. So you'll get this back on Wednesday? Yep, and we'll have a little conversation about how we did. Tomorrow's lab is, we're in a new phase of labs, so Dr. Harris is teaching lab tomorrow. Dr. Harris is our inorganic / analytical expert, and so he's taking over. He teaches second semester GChem, so just awesome that we have his level of expertise as a NASA expert here, so asking lots of questions. Again, I really my expertise is pretty narrow. It's called carbon. He knows the rest of them. So make sure you ask lots of questions of him, because super knowledgeable in lab and just also in lecture. So, okay, so we're jumping into a new. We really have 5 chapters left, and we're going to look at the next block, if you will, as building the concept of chemical bonding. Okay, how is it that 2 atoms come together to form an actual bond? What do I know about that bond? What aspects of that bond are predictable that I could use that to make molecules, to make connections between atoms with similar properties? So I really like this block of 3 chapters, because it ends with real practical chemistry. Remember, bonding is 2 electrons coming together. 1 atom bringing an electron, 1 atom bringing an electron, and as poly. So we basically have 2 electrons coming together into this form, forming a bond, and we draw a line or whatever. So we get into some really fun things. We get into electronegativity in this chapter. We get into electron affinity in this chapter. Then we're going to get into polarity. Then we're going to get into VSEPR. Then we're going to get into molecular orbital theory and hybridization. Super fun segment. I'll be honest with you, this is my favorite chunk of GChem. Okay? So the next 3 chapters, we've kind of slogged through thermo together, right? And everyone loved thermo. I had more emails over thermochemistry than any other chapter, all chapters combined. All right? I know there's a lot of frustration with thermo. I get you on that. All right? Wait until you take thermo at the next level up. It even gets more bizarre and more difficult and more frustrating. Thankfully, I don't think very many of you in this room are going to do that. That said, it's important to understand heat movement, right? From hot body to cold body, systems surrounding, all the stuff you loved talking about, endothermic, exothermic, right? We made it through that. This now, again, goes into a really fun level of 3-dimensional space and practical bonding theories, all right? So I like this. Again, like I said, I enjoyed this. I enjoyed teaching this section. I really enjoy this section because this section, like no other sections, the first 2 or the second 2, this third one sets a foundation for organic chemistry. So as an organic chemist, as a passionate organic chemist, that's why I think I like this section the most, because it's a very powerful foundation, okay? Dr. McGallis will review a lot of the stuff that we bring out of here with polarity, polar bonds, electronegativity, VSEPR theory, what's an sp3, what's an sp2, what's an sp, all that comes up in organic chemistry. Even comes up in advanced organic chemistry. So this is a really foundational chapter. Now, when we look at the periodic table hasn't been around that long, okay? Last half of the 19th century is really when the periodic table began to emerge. We are standing on literally the shoulders of giants before us. It's easy for us to count from 1 to 118 because we know now that that's all we're doing. We're either counting electrons or protons. It doesn't matter. Neutrons are all over the place. But where did the periodic table come from? This is an important piece of chemistry history. So we're just going to spend a couple minutes talking about the history of the periodic table because it's important. Again, we didn't always have this. And you'll even notice that this one is different than that one. This one has gaps at 113 and 115 and 117. That one has them actually filled in, okay? And so this one still calls this one uquath. That one calls it FL. I have no idea what FL stands for, okay? So you can see that the periodic table changes, and historically it's being updated.
I do believe all 118 are now named, so I could probably update that one with the correct one. Again, I don't know the names of those down there in the lanthanides, below the lanthanides and the actinides. That's not my chemistry. My chemistry is really simple. It's carbon, nitrogen, and oxygen. So that's really a nice place to live. 3 atoms is all I have to worry about. But the rest of them are there. But where did this thing come from? Where did the periodicity come from? Well, if you look at the elements historically, you look at some of the ones that we knew in ancient times, and this is kind of my dad was a history teacher, and so I think I just kind of gravitate towards history. I like it, I enjoy it. But you look at ancient times, which ones do we have? Well, right here, copper, silver, and gold. Now, if you remember, copper, silver, and gold are really unique elements. They're unique elements because they sit right here with their D block with 9 electrons. So what they do, if you remember, they borrow one from the S block in order to fill the D block, and so they mimic royalty, even though they're not royal. It's kind of cool. So that makes them really not very oxidizable. In fact, gold doesn't oxidize, right? So it's beautiful, and it has this beautiful look. Silver, when it's polished, has this beautiful look. Original mirrors were silver-plated glass, right? So, and hyper-polished copper. Some of these things what do you actually look like? You ever think we take mirrors for granted? Most people only saw their reflection in still water before the invention of polishing metals or plating silver to glass. So those are some of your ancient elements right there, ancient times. And then you can see the Middle Ages. Which ones came out of the Middle Ages? Well, zinc and platinum and bismuth, phosphorus. Oh, phosphorus. Maybe, just maybe, we could take phosphorus or sulfur and mix it with mercury and produce gold. Okay, so you get a lot of your amalgamas, a lot of your ancient types of chemists trying to make gold, basically, trying to do the impossible. But sincere about it. They were very sincere in their progress, and we actually learned a lot from their failures. And a lot of chemistry came out of the failures of those original experiments. And then from the Middle Ages, then we move up into the 18th century, and you can see that a lot was filled out in the 18th century, which is where we're going to begin to build the periodic table. Okay. Towards the end of the 19th century, then we started to see some of the more difficult ones to find, like technetium, and technetium right here was found really late in the game. It's because technetiums are a really weird element. It's man-made. We don't find it naturally. Why? Well, it's got a weird electron structure, so it sits there. And anything that's hollow up here is man-made. It's synthesized. It's not. We don't find it in the crust of the Earth. Okay. Anything that's blue, of course, is going to be liquid at room temperature, and anything red is going to be a gas. So that's kind of the way it works. So these here were some of the last to be found, and you can see that over here. Why was that? Well, because they didn't react with anything. So how do you find something that doesn't react? Because the rest of these were found from doing chemistry, actually doing reactions. And we'll see that trend kind of progress. And the final phase of this understanding of the periodic table came from after 1965. What happened in 1965? You want to take a stab at it? What did we develop in the 1960s? Bombs. Okay, that came out of, yeah, that was actually 1940, Manhattan Project. We were working out the nuclei. Can we split the nuclei? Can we fuse nuclei? Okay, so particle accelerators happened in the 1960s. And so particle accelerators is how we actually were able now to make these synthetic, and so you can see that that's where we are today. And the thought with this is, once again, can we get past 118 up to the G block elements? So it's kind of interesting, all right? So that's it. But where did it start? Where did the actual construction and development of the periodic table start? Some of the very first work in this dealt with similar reactions of barium, calcium, calcium, and strontium. These three right here. In the Greek mind, there's something called, it comes from the Greek mind, but it's in Latin. It's called the omnitriumph perfectum. Some of you might have known the omnitriumph perfectum. I'm a big fan of the omnitriumph perfectum because I think we're wired for triads. I think it's natural to us because we are a triad. We are body, soul, and spirit. But if you think about it, it rolls off your, really rolls off your mouth easy. TNT, DNA, RNA, COC, right? FBI, Larry, Moe, and Curly, the Three Musketeers, Peter, James, and come on, John. Okay, we are wired for triads, and so it doesn't surprise me that the early development of the periodic table was looking for triads within the elements. So the first triad that was pointed out, and I don't speak French, so I won't butcher his name, but it's something like Johann Daubrier, good enough for me, was one of the very first people that actually worked with, hey, there's a relationship here between calcium, strontium, and barium. Maybe that relationship comes from that triad. And so that was the original thought, that maybe there's a relationship between these atoms, or these elements, if you will. And so that was the very first, in 1817, you can see that triad was proposed, okay? Again, that was the beginning of the search for the relationship between us. Now, you have to remember, we didn't know that calcium had 20 protons and 20 electrons. You and I look up here and we see the blue 20 and we go, oh, well, duh. But they didn't know that. They didn't know that strontium had 38 electrons and 38 protons, or that magnesium had 12 electrons and 12 protons. So they didn't understand that connection. So the next leap was actually, I think, a fascinating leap. Even though he was ridiculed and mocked, because he was a musician, not a chemist. I mean, he dabbled in chemistry, but he was a musician, and I loved his sincerity, and that was really Newland. Newland said, wait a minute, it seems like about every 8th element, there's a relationship. Well, we might know that today as going down the periodic table. It seems like calcium has a similar reaction to strontium and magnesium. See, there's 8 between magnesium and calcium. So he proposed the very first periodic table, completely wrong, but nonetheless it was built on more of a musical idea of 1 and 8. So 1 through 7 being, right, the notes, the chords, and then the 8th being the next new, so right, the next C, if you will. So if you start with C, you're going to go up through B, which is 7. Your next one is 8, which would be the next C. And it made sense. And again, he was really mocked by this. It was kind of sad. But he was just trying to put things together. But here's the problem. Notice what's the problem. Anyone want to see what the problem is? Take a stab at what the problem is. Is that the periodic table? What comes after hydrogen? Where's helium up there? Yeah, because we didn't have helium. Okay? So what comes after nitrogen? Okay, what comes after oxygen? Yeah, so he puts it down here, not up here, because why? Well, we're missing something. We're missing quite a bit, right? So here was the genius of the discovery of the periodic table. It comes from Mendeleev. Really, Mendeleev is really considered the father of the periodic table. And here was the genius of what this Russian chemist did. He said, wait a minute, I don't think we have all the elements. So instead of taking the elements that we know and trying to string them together, why don't we group them in their similar reactivities, and we'll probably have some gaps. And that was really the genius of Mendeleev and how that periodic table actually became what we have today. In fact, any theory, if it's a good theory, should have predictability. If this, then this. Okay? And so I think some of his predictions in the construction of the periodic table were brilliant. I'll show those to you up here. Okay? So really in 1871, again, we do have combustion, we do have steam power, we don't have hydraulics quite yet. We're still doing science by candlelight. So this is pretty primitive, okay? Most people are riding horses or walking and wearing leather shoes, okay? So this is pretty primitive. But really what happened with Mendeleev is he said, wait a minute, instead of just stringing it all together, I'm gonna place these in order of their reactivity. And so he said, again, he noted that astatine actually belongs under phosphorus, not silicone. He says silicone, there's something under silicone. There's something under silicone that we don't know what it is. Okay, germanium, we know it today, but we didn't know it today, so it's missing. And so, again, this became the original periodic table, and when he published his paper in 1869, it looked like this. Okay, so that's actually an actual picture out of his original journal. And you can see that there were gaps. So right in through here, you see that there are gaps right here, gap here, gap here. We just didn't have those elements yet. So I'm gonna align these with their reactivity, and just assume that we're actually missing a few. We just haven't found them yet. And it turned out that was true. But here's what he did that I think was genius. Like I said, any theory, if this theory is correct, then he should be able to predict. And here's what he did. He left the gaps in this, and using that, he predicted what this Eka boron, what the compound under boron should look like. He proposed Eka aluminum, Eka silicon. What do these things look like? What should they, if they exist, if they're real, what would they look like? What would their properties be? And again, this becomes the genius of what happened with that. So then 10 to 15 years later, we actually found these, and look at his predictions, okay? So this is predicted. Here's what he predicted. Eka silicon, we know it now as germanium. He said it should have an atomic mass of 72, if it exists. It should have a density of 5.5. It's pretty cool. It should have a specific heat. There you go. Oh no, that's thermochemistry. Specific heat of about 0.305. It should have a high melting point, be dark in color. It should have an oxide of O2. The density of the oxide should be about 4.7. Its formula with chlorine should be Cl4, and its boiling point of the chloride should be a little bit under 100. And look at germanium. So I think, to me, that is the genius of what Mendeleev did, right? He brought in the thought that, well, we're probably missing some, but if it is real, if that is, here's what we should be looking for. And the previous slide said within 10 to 15 years, those were found, because now we know what to look for, okay? So when you go back to that historical nature of the periodic table, here, notice where we're at in our periodic table. We're right in through here, okay? And you can see that these were all filled in now that we had some predictions of what we're actually looking for. So I think that is kind of the cool thing on the development and the genius of the early chemists being sincere about trying to fill this, or trying to produce what we know today, again, as the periodic table. The other one that's kind of fascinating here is, oh no, that's the same one. And again, I have another slide of this, that the other ones that he predicted is similar. Like, wow, that was really cool that he was able to do that. Because those are pretty close to what we actually know as those compounds, okay? So, today, we have the periodic table. When I go teach in the classrooms around the valley, I do a little thing teaching them how to make the true periodic table. So we cut them all out with scissors and we tape them together, and we end up with this beautiful thing called the real periodic table, which is that ribbon that I've shown you here. So I have the school children, school kids, middle school, junior high, and lower high school actually make this, because I want their eyes to see the real periodic table, because it's really hard to unteach that. Okay, and again, that's because, like I told you before, it fits on a nice square piece of paper. Okay, so all it is counting from 1 to 118. I've said that so many times that you should probably get tired of me saying that. So now you're experts in S block elements, F block elements, D block elements, and P block elements. Okay. So they're going to have a similar reactivity, similar reactive pattern, because again, their electrons are in similar locations relative to the other electrons within the atom. Okay. So again, that's the complete periodic table, and I still don't like that periodic table. This even makes it worse, even though that's more correct, but still, look how far it puts, 1 away from 3. It's like, oh my word, or 1 away from, it's just like, it just doesn't look like that. So that's isn't that pretty? That's just pretty too. All right, it just looks like. So here's hydrogen, here's helium, lithium, boron. Ooh, coming around the horn here. Oh wait, lithium. Where's lithium? There it is. boron. Who am I missing? Oh, beryllium, yeah, or beryllium. Boron, oh, there it is right there. Just a moment of silence for carbon real quick here. Look at that thing right there. 6 electrons and 6 protons. Isn't it amazing to have so much fun with 6 electrons and 6 protons? And carbon only uses 4 of its electrons. Imagine if it used all 6. Maybe in heaven, carbon will have all 6 electrons used. It doesn't even use the ones in the 1s2. It just uses the one in the 2s2, 2p2, and hybridizes them into an sp3. It's oh, it's amazing. Yeah, it's so cool. Yeah, so then we just go around and blah, blah, blah. Kind of more boring ones over here. Then there's silicone, kind of important one. And then we come back around to our Ds, and then finally up to the lanthanides and the actinides. Someday, maybe we'll complete this all the way around to get to 118 of nobility, okay? So that's it. Now, what comes out of this chapter that's really important? 4 things. 4 things you should be thinking through as we go through that are pragmatic applications of periodicity, okay? Number 1, how big are atoms? How big are ions? Why are cations smaller than anions? Why are anions much bigger than cations? Okay? Why is calcium bigger than sodium, which is bigger than lithium? Sizes. Okay? Why do I actually go down in size from left to right across the periodic table? That seems counterproductive. I understand why aluminum is bigger than boron, because aluminum has 13 electrons and boron only has 5. But why is silicon smaller than aluminum? Why is phosphorus smaller than silicon? It has more electrons. Shouldn't it be bigger? You have more, so it should, well, we probably should understand why that is. What's that trend come from? Right? Big pictures, this is the effective charge of the nucleus, and we'll break that down and look at that. What about ionization energy? How much energy does it cost for sodium to lose an electron? How much energy does it cost for sodium to lose 2 electrons? Does sodium want to lose 2 electrons? How badly does sodium want to look like fluorine? Well, it's probably going to be pretty expensive to make sodium look like fluorine. So ionization energy, okay, the trends there. Electron affinity and electronegativity. I've already gone through electronegativity a little bit and introduced it to you, but it is one of the absolute most important concepts that we take out of this chapter, period. It transcends all of chemistry. Okay? I think it's one of the most important foundational axioms of chemistry is electronegativity. So we probably should understand that. It's probably why it's in bold and red up here on my PowerPoint slide. Okay, so it's to me one of the big ones that I want you to master. We've already memorized it, right? 4.0, 3.5, 3.5, 3.0, 3.0, 2.5. How do we then use that in the sense of chemical bonding and bonding theories, okay? So, sizes of atoms. How do we know how big an atom is? Well, the way we typically do this is we don't actually know the diameter of an actual atom, so we take 2 atoms and we divide it by 2, okay? So that's how when we say this is the actual radius or the diameter of the atom, it comes from pairing those 2 atoms up and then taking half and half and cutting that in half. Because again, if the electron cloud is just kind of out there buzzing around, how far out of the cotton ball do you go to still call it part of the atom? So the way it's actually done again is taking the distance between 2 nuclei and cutting that in half as the radius, if you will, of the actual nuclei. Okay, and so you can see that that's basically done here with H2 with hydrogen. Okay, so we take half of the diameter for the radius. Right? So the effective nuclear charge is really, the effective nuclear charge is how much the nucleus, where all the positive protons are housed, how much they feel those outer electrons. Okay? So let's say we're sodium. Sodium has 11 protons in the nucleus. It has 1 electron in its valence shell way out there. But between the 11 protons and that 11th electron, what do you have? You have 11 protons in the nucleus, and you have 1 electron way out there in its valence shell, the 11th electron. What do you have between it? What is it? The other 10 electrons. Okay? So you have 10 electrons between that outer electron and the nucleus. So there's a way to quantify that effect. How much of the shielding effect is there between those other 10 and that little one way out there in its valence shell, okay? And we call that the Z effective, all right? This shielding, if you will, of the outer electron. And so here you have 10 electrons, and here you have the electron that we're actually worried about, because that's the electron that wants to go and do work. Sodium only wants to lose 1 electron, so it's probably the one we should probably be focused on. That's what we do, okay? So we work with that, and we say, what's the effect of those 10 electrons versus the 11th electron versus the 11 protons in the nucleus? Pretty exciting stuff, I know. But that's what we're looking at in order to understand how we have the electron's cloud, or the size of the ion or the atom itself, okay? So that's what we see, all right? So here's that little electron way out there. This is its density, right? It's electron density out there. And so you can see that the density is mostly those inner electrons, and then the outer electron, which we're going to call our valence electron when we get to bonding, okay? So the Z effective basically is Z being the atomic number. It's the blue number up there, all right? S is the screening constant, usually close to how many inner electrons there are. And it's all kind of a-ish, kind of rough, all right? But it does give us an idea as to why we have different sizes. Like I said, why is it that we get bigger as we go down the periodic table and we get smaller when we go from left to right, okay? Going down makes sense, going left to right might not make sense unless we understand the Z effective, and that's exactly what the trend is that we see, okay? So there's this effective charge that outer electron, the outer electrons feel from the protons in the nucleus, but they're shielded again from the more core or the noble electrons. Okay. So here's your trend. We're getting bigger as we go down, but we're going smaller as we go from left to right. Okay. And maybe you can kind of get a sense of what's going on there. As we're going from left to right, you're increasing your number of protons, right? So you're getting more positive in the nucleus, which means you're actually pulling in on those electrons outside of, that are out there buzzing around. So that's why we see this trend, even though we're having more electrons from left to right, but our radius is going down slightly, okay? Because again, there's more protons pulling on those electrons, bringing them closer into the nucleus, which makes the radius smaller, okay? So that's your overall. So radius tend to decrease from left to right, good trend to memorize, okay? Decrease from left to right, increase from top to bottom, okay? And that's makes sense probably if you remember back last chapter with the quantum numbers. The quantum just takes more energy, different energy level. If I have to go into a 3p versus a 4p, 4p is just larger and it's just going to have a more area to fill. And so that's why the trend there is increasing from top to bottom, decreasing from left to right. Okay? Yeah, there we go. And that's just a graph to show your effective nuclear charges here going down. So you can just see that kind of sucking in on those outer electrons. Cool, right? Good stuff, huh? Now, ions, if you think about sodium, if sodium loses 1 electron, it mimics nobility, it mimics a neon element. So you'd expect once it has that electron out there in the 3s1, if it can get rid of that, it doesn't have 3s1 anymore, it has the 2p6 full. Okay? So with that, you can see sodium all of a sudden as an cation, as an ion, gets quite a bit smaller than sodium as a metal. All right. Now that becomes important next semester when you guys start talking about spatial arrangement of the lattices of these compounds, which is really fun. But that's more Dr. Hare's realm, not my realm, and so he'll work with you on that. So you can see that sodium as a metal has a radius of 1.54 angstroms. This might be picometers, nothing that's angstrom. But as a cation, okay, it's 0.97. Magnesium, even though it's larger right here, notice when it loses 2 electrons, it even gets smaller. Okay? Again, it's the effective nuclear charge is affecting that, pulling those electrons in once it gets rid of those big electrons on the outside. Okay? And by the time we get to aluminum, which is even bigger than magnesium, you're getting pretty small. So the trend is, as you go from metal to cation, you get smaller, okay? It's the opposite with the anions. Notice the anions, oxygen, let's go to chlorine. Chlorine's more fun to look at. Chlorine as an actual element is 0.99. When chlorine, who wants an electron more than anybody else on the periodic table, when chlorine takes that electron, gets that electron, what does happen? Well, the overall size of chlorine actually expands, it gets larger. So as you see here, cations are small, anions are large. So what's going to happen with that when you get into your, when you actually get into using this chemistry, this is where you'll see when you have something like sodium chloride, okay, this is the sodium, and this is the chlorine. And so what happens is sodium chloride then begins to form some form of a lattice. And so we call that lattice, if I'm going to do it correctly, let's go ahead and do this. So what we do with the lattice is we say, oh, well, the lattice as a whole becomes 1, 2, 3 sodium, 4 sodiums, and 4 chlorines. Oh, so it's 1 to 1. Or it's NaCl, okay? And so that's really what happens. The cations become small and they fit in these little pockets. The chlorine are larger, and so there's a spatial arrangement to the sodium and the chlorine. And that comes from, again, the fact that the anion is larger than the cation in the sizes of these ions. Okay, so this is kind of a cool little thing here. Okay, now let's move to ionization energy. 4 things we need to talk about with this chapter. One of them is the sizes we dealt with. Now we're going to talk about the ionization energy. But before we just jump in, let's look at what we should expect up here. For example, how much would it cost chlorine to lose an electron? Well, it's going to cost a lot. Because chlorine doesn't want to lose an electron. It doesn't really want to look like sulfur. Chlorine wants to gain an electron. So we'd expect the ionization energy of chlorine to be pretty high. Ionization energy of potassium. Man, potassium, if it loses 1, it's 18. It mimics argon mobility, okay? But to lose a second one, it's probably going to cost me a lot of energy, right? Magnesium, how many does it want to lose? Well, if it loses 1, it looks like sodium. If it loses 2, oh, again, it mimics mobility. So we should probably see a trend there, or a line there of energy associated with ions, or with these elements wanting to lose electrons. And that's pretty much what we see. How much energy is required to remove an electron? How much does it cost to remove an electron from an atom? That is my ionization energy, okay? First ionization energy is the energy required to remove the first electron. The second ionization energy is the energy required to remove the second electron. So what do you think the third ionization energy is going to be? Yeah, the amount of energy to lose 3 electrons. So you'd probably expect that to be pretty low, or lower for aluminum than you would for magnesium. Aluminum doesn't mind losing 3 electrons because it wants to mimic mobility. Magnesium doesn't want to lose 3 electrons because it only wants to lose 2. So we'd expect there probably be some kind of an energy shelf between once I lose enough electrons to mimic mobility, and that's pretty much what we see here. So in going down, here's sodium. Sodium to lose an electron is 495 kilojoules. Okay, so if you look at sodium, it does cost it some energy to remove that electron, but it's not that much on the relative scale here. That's not much energy. But notice, for sodium to lose a second electron, to be Na2+, it's going to cost you a lot of energy for sodium if you really want sodium to look like fluorine. Okay, and you can see 4,562 instead of just 495. Okay. Jump down to magnesium. Magnesium wants to lose 2 electrons, so yeah, it costs 1,451. But man, for magnesium to lose 1 more electron, it's going to cost you a lot of money. Okay? Likewise with aluminum. Aluminum wants to lose 3, doesn't want to lose 4. So you can see that there is a shelf here of energy, okay? Of energy, the amount of energy required to remove that electron past ionic nobility. Okay? Any questions on that? Does that make sense? kind of see that trend. Yeah. Cool, huh? Yeah, really cool. So that leap is just impractical. So typically we don't see those, right? Now, what about the anions? That's one of the things that we will see. Anions are a little bit different. They don't like to lose electrons. Chlorine doesn't really want to lose. It can. It doesn't really want to. It wants to gain an electron. But we'll see there's something between, say, like chlorine and sodium. Okay, there's the relationship between their energies, one to lose and one to gain, and we'll talk about that. Now, here is the first trends in the first ionization energy. Helium is the highest to lose 1 electron. Helium really does not want to lose an electron. It doesn't want an electron out of its n equals 1 principal quantum level. It's happy with it in the n equals 1. Hydrogen doesn't really want to become a cation, but it does cost energy to do that. So you can see though, once I get down to lithium, sodium, potassium, rubidium, and cesium, they're really fine with losing electrons. In fact, if you look at that trend, they're very, very reactive. Okay? So one of the things I like to show students is how much does sodium and lithium and potassium, how much do they really want to lose an electron? So let's watch this little British video here. So this video, it actually is a really good teaching video. It does have I'm not a big fan of like crass stuff. It does have a kind of a British euphemism in it, so I do apologize for that. But I think we're mature enough to get past that. So hopefully this won't be. Turn the volume on this thing. Where's my volume? Ah, there we are. Okay, let's see if this will play. No, hang on. So now again, what this is, so keep this, keep in mind what's going on here. This is how much atom wants to lose an electron, okay? So when you take lithium, sodium, potassium, rubidium, and cesium and add them to water, you're gonna lose an electron. That's what's going on with this. That's why I want to show you this, because it's really important. If you
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, my friend. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad!
Now, 2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes! Well, that is more like only on Brainiac do you get that kind of science. But I believe we can go one better. There's one more alkali metal we can really use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
Yeah, I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it. Good luck.
Thank you.
Okay, John, go for it.
Warning, extreme danger, clear the air.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, frankium. But for some reason, they wouldn't let us have any of that. So there you go. Today's lesson.
Never mix alkali metals with water.
Okay, so what's happening there? Why is it so explosive? Why is cesium and rubidium so massively more explosive than sodium and lithium? No? Yeah.
Because the atomic radius is larger, so you have a big span.
So as lithium being smaller, you see it, that electron out there is being held in by the nucleus tighter. As you get to sodium, it's bigger. That electron's easier to give up. As you get to potassium, rubidium, by the time you get to cesium, that outer electron is really easy to give up. So if you put it in water, water says, I want that electron, and it just takes it. And that's what we're seeing. That's an exothermic reaction, by the way. That's what those are. That explosion is giving off energy to the system, right? To the surroundings. So we see this trend of reactivity, and that's what you're seeing. When I was in high school, my teacher took a golf ball size hunk of sodium out on the football field and put it in a 55-gallon water thing. It was super cool. I remember as a kid, and we all stood there in bleachers, and he threw it in there, and the whole thing just looked big plume of water, right? So you're seeing that reactivity, and that's just the move. That's really all that is the loss of an electron. All you're doing is you're going from sodium metal to sodium plus. That's it. That's all these reactions are. Loss of one electron. Okay? But that's that first ionization energy is you're seeing the power of really losing that electron. Sodium really wants to lose an electron. In fact, you can't find sodium metal in the crust of the earth. It doesn't exist. It's either an oxide or chloride or some other form because it is so reactive. Cesium is the most reactive. Cesium says, I want to give up an electron more than anybody on this periodic table. And that should make sense because who has the lowest electronegativity? Cesium. Cesium says, no, take it. I really don't want it. I'm really happy. I've got 54 other electrons that look like nobility. I look like xenon when that one's gone anyways. And it's way out there. Go ahead, take it. I don't need it.
What are the chemical properties of like this reactive alkali metals once they've already reacted?
Yeah, well, like what they're forming there is hydrogen gas and basically cesium hydroxide.
Right.
So that's what it's actually forming.
But then can you use this hydroxide to make further products?
Yeah, absolutely. Yeah, absolutely. Because remember, cesium hydroxide is a strong base. You take a strong.
Have the electron configuration of xenon at that point?
It mimics it. Yeah, it mimics it in an electron, but it'll always be true to itself, right? It's always going to have 55 protons. But we don't work with proton chemistry, right? We work with electron chemistry. So it really does want to mimic that nobility. So it really would rather have 54. Yeah. Or another way to look at that, the hydroxide would really like to have cesiums. And cesium says, okay, cool, you can have it. Okay. It'll cost you some energy, but you can have it. Okay? So anyway, it's a good little kind of an analogy of how much energy is really associated with the first ionization, or at least the alkali metal family here, alkali earth metal family here. You can see that. Okay. So that said, electron ionization has a few trends that are probably going to hopefully make some sense. So let's take a look at some of these trends here. One of the trends is what's going on with my Z effective. Well, like I said, that's what's causing the size to go down from left to right across the periodic table. But we also might be able to come up with some trends that maybe are here between this line and maybe between this line, okay? Like we did with our electron configurations, maybe those electrons, maybe it's going to be easier to give up an electron if I'm iron, so that I have 1, 2, 3, 4, 5 all spin unpaired in my 3D orbital than for manganese, which says if I give one up, I don't really gain a whole lot. Maybe we'll see a line here. And so when we look at the actual trends, turns out there are some trends with how easy is it for something to give up an electron. So here's helium, doesn't really want to give it up, so it doesn't really do a whole lot for us. But notice from lithium, beryllium, but all of a sudden I go down to boron. Why did I drop down? Why is it easier for boron to give up an electron than beryllium? Anyone? You got it. So we have to put a P. So right, we're 1s2, 2s2, 2p1. So to lose an electron out of the 2p1 and to have a full, if you will, 2s, that just doesn't cost as much energy. Likewise, when you go from your next jump up to, okay, so there's boron, there's carbon, there's nitrogen. Oh, look at oxygen. Oxygen, it's easier to lose an electron than nitrogen. Why? Same trend. This is 1s2, 2s2, 2p1, 2p2, 2p3. Now all of a sudden I have to spin paired. So to lose that, to go back to unpaired, it just doesn't cost me much energy. So again, you can see that those trends are there, those anomalies, if you will, all across the periodic table. Okay, again, all we're talking about is the movement or the electron, how much does it really cost in energy to remove an electron from an atom. Okay? And so that trend is pretty consistent there across the board. All right? Pretty exciting day. We did our history of the periodic table, we did our ionization energies, and what else did we do? We did our sizes of ions and cations. So now we're going to bring up electron affinity, electronegativity on Wednesday, and then we'll have a worksheet on Wednesday to solidify all this awesome information.